Tonight, we're going to explore one of the most remarkable achievements in the history of human science. We're going to discover how, after centuries of theoretical predictions and decades of technological preparation, humanity finally captured an image of something that was once thought to be fundamentally invisible. We're going to understand how a global network of telescopes spread across continents from the frozen expanse of Antarctica to the volcanic peaks of Hawaii worked together to peer into the heart of a galaxy 55 million light years away and reveal the shadow of a supermassive black hole. By the end of this journey, you'll understand the theoretical foundations that predicted what we would see, the engineering marvels that made the observation possible, and the painstaking years of data analysis that transformed mountains of hard drives into a single historic image. This is the story of the Event Horizon Telescope and how humans finally saw a black hole. Before we begin, if you find yourself relaxing into this exploration of cosmic wonders, a gentle tap on the subscribe button would help this channel continue bringing you these deep journeys through space and science. Now, let's travel back through the centuries to understand how we came to know that black holes exist at all. Part 1. The Impossible Dream. For most of human history, the idea of a black hole would have seemed like the ravings of a madman. How could there exist an object so dense, so gravitationally powerful, that nothing could escape its grasp? How could space and time themselves become so warped that the very concept of escape becomes meaningless? And yet here we are, in an age where we have not only proven the existence of these cosmic monsters, but have actually photographed them. The journey to that photograph begins with understanding what makes the achievement so extraordinary. A black hole, by its very definition, does not emit light. It cannot be seen in the traditional sense. The event horizon, that invisible boundary marking the point of no return, swallows everything that crosses it, including the photons that would otherwise reveal the black hole's presence. How then do you photograph something that is fundamentally dark? The answer lies in what surrounds the black hole. Supermassive black holes at the centers of galaxies are rarely lonely. They are typically surrounded by disks of superheated gas and plasma, material that has been captured by the black hole's immense gravity but has not yet crossed the event horizon. This material, spiraling inward at tremendous speeds, heats up to billions of degrees and glows brilliantly across the electromagnetic spectrum. It is this glowing material, backlighting the black hole like a cosmic lamp, that allows us to see the shadow cast by the event horizon. But even knowing what to look for, the technical challenges remained staggering. The supermassive black hole at the center of the galaxy, Messier 87, the first target successfully imaged by the Event Horizon Telescope, lies approximately 55 million light years from Earth. At that distance, even an object containing 6.5 billion times the mass of our Sun appears incredibly small in the sky. The angular size of the black hole's shadow, as seen from Earth, is roughly 42 microarcseconds. To put this in perspective, this is equivalent to trying to photograph a donut on the surface of the moon from your backyard. It is equivalent to reading the text on a newspaper in Los Angeles from a vantage point in New York City. No single telescope on Earth, regardless of its size, has the resolution to resolve such a tiny object. The fundamental physics of optics dictates that the resolution of a telescope is directly related to its diameter. To achieve the resolution necessary to image a black hole's event horizon, you would need a telescope with a diameter approximately equal to the diameter of the Earth itself. Obviously, constructing such a telescope is impossible. But what if, instead of building one impossibly large telescope, you could link together many smaller telescopes spread across the planet and make them work as one? This is the core insight behind the Event Horizon Telescope. By precisely coordinating observations from radio telescopes on different continents, recording the incoming signals with atomic clock precision, and then combining those signals mathematically, scientists can synthesize a telescope with an effective aperture spanning thousands of kilometers. The technique is called very long baseline interferometry, and while it had been used for decades in radio astronomy, applying it at the wavelengths and precisions necessary to image a black hole required pushing technology to its absolute limits. The Event Horizon Telescope collaboration, when it captured its historic image in April 2017, linked together 8 radio observatories at 6 geographic locations. These facilities stretched from the Atacama Desert in Chile to the volcanic summit of Mauna Kea in Hawaii, from the Sierra Negra in Mexico to the Pico Veleta in Spain, from the Atacama Pathfinder experiment alongside the Atacama Large Millimeter Array to the South Pole Telescope, standing alone on the frozen Antarctic plateau. Together, these telescopes formed a virtual instrument with a diameter equivalent to that of Earth itself, achieving an angular resolution sharp enough to see the shadow of a supermassive black hole for the first time in history. But resolution alone was not enough. The observations had to be precisely coordinated, with all telescopes observing the same target at exactly the same time, their recordings synchronized to within fractions of a trillionth of a second. The data collected was so voluminous that it could not be transmitted over the internet. Instead, it had to be physically shipped on hard drives to central processing facilities, where specialized supercomputers would spend years combining and analyzing the signals. The total data collected during the April 2017 observation campaign amounted to approximately 3.5 petabytes, enough to fill tens of thousands of standard hard drives. And even after the data was collected and combined, the challenge of creating an image remained. The Event Horizon Telescope does not produce photographs in the conventional sense. Instead, it measures the interference patterns between radio waves arriving at different telescopes. These patterns contain information about the structure of the source being observed, but extracting that information requires sophisticated algorithms and careful analysis. Multiple independent teams, using different software and techniques, worked separately to reconstruct images from the data, comparing their results only after they had reached their conclusions to ensure that the final image was not an artifact of any particular method. When those teams finally compared their reconstructions and found that they had all arrived at the same basic structure, the same ring-like emission surrounding a dark central region, they knew they had succeeded. On April 10, 2019, the Event Horizon Telescope collaboration held simultaneous press conferences around the world to reveal the first image of a black hole. The image showed exactly what general relativity had predicted over a century earlier: a bright ring of emission, brighter on one side than the other due to the rotation of the infalling material, surrounding a dark shadow where the event horizon's gravity prevents any light from escaping. The dream that Einstein himself thought impossible had been achieved. Humanity had looked into the abyss, and the abyss had looked back. Part 2. The Theoretical Foundation. To understand what the Event Horizon Telescope revealed, we must first understand how scientists came to predict what a black hole would look like in the first place. The theoretical foundation for black holes stretches back over a century to the revolutionary work of Albert Einstein and the mathematicians and physicists who explored the implications of his general theory of relativity. In 1915, Einstein published his general theory of relativity, fundamentally reconceiving our understanding of gravity. In Newton's classical mechanics, gravity was a force acting instantaneously across space, pulling objects toward one another in proportion to their masses and inversely proportional to the square of the distance between them. Einstein's theory replaced this picture with something far more profound. In general relativity, massive objects do not exert forces on one another through some mysterious action at a distance. Instead, they curve the fabric of space-time itself, and other objects move along the straightest possible paths through that curved geometry. The implications of this new theory were difficult to calculate. Einstein's field equations, which describe how matter and energy curve space-time, are extraordinarily complex. They consist of 10 coupled nonlinear partial differential equations relating the curvature of space-time at each point to the distribution of matter and energy throughout the universe. Solving these equations exactly is possible only in highly symmetric situations, and even then requires considerable mathematical sophistication. Consider what Einstein had accomplished. He had replaced Newton's simple inverse square law of gravitation with a geometric theory of unparalleled elegance. In Newton's picture, the Earth orbits the Sun because the Sun exerts a gravitational force on the Earth, pulling it constantly away from straight-line motion and bending its path into an ellipse. In Einstein's picture, there is no force. The Sun's mass curves the space-time around it, creating a kind of valley in the fabric of reality. The Earth simply follows the straightest possible path through that curved geometry, a path called a geodesic. What Newton interpreted as a force, Einstein revealed as geometry. This geometric reinterpretation had immediate consequences. It explained the precession of Mercury's orbit, a tiny discrepancy between the observed motion of the planet and the predictions of Newtonian mechanics that had puzzled astronomers for decades. It predicted that light, despite having no mass, would be deflected by gravity, bent as it passed near massive objects. This prediction was confirmed during the solar eclipse of 1919, when British astronomers observed that stars near the Sun appeared slightly displaced from their normal positions, their light bent by the Sun's gravity exactly as Einstein had calculated. But the most profound implications of general relativity concerned what happens when matter is compressed to extreme densities. Newton's theory says nothing special about very dense objects. The gravitational field at the surface of a star is given by the same inverse square formula, regardless of whether the star is a diffuse red giant or a compact white dwarf. Einstein's theory, however, predicts that as matter becomes more and more concentrated, the curvature of space-time increases, eventually reaching a point where something remarkable happens. Einstein himself initially produced only approximate solutions suitable for describing weak gravitational fields like those in our solar system. He was pleasantly surprised when, only months after publishing his theory, a German physicist named Karl Schwarzschild found an exact solution. Schwarzschild accomplished this remarkable feat while serving in the German army during World War I, stationed on the Russian front. In December 1915, he sent his solution to Einstein in a letter, deriving the exact description of the gravitational field surrounding a spherical, non-rotating mass. Tragically, Schwarzschild would not live to see the full implications of his discovery. He died in May 1916, possibly from the autoimmune disease pemphigus, which he developed at the front. He was only 42 years old. The Schwarzschild solution, as it came to be known, described space-time in a way that had profound and initially puzzling consequences. At a particular distance from the central mass, a distance that came to be called the Schwarzschild radius, the mathematics became singular. The equations appeared to break down, producing infinite values for certain quantities. For a long time, physicists assumed this singularity was merely a mathematical artifact, a quirk of the particular coordinates Schwarzschild had used, rather than a genuine physical phenomenon. The Schwarzschild radius for any object can be calculated from its mass. For our Sun, the Schwarzschild radius is approximately 3 kilometers. This means that if you could somehow compress the entire mass of the Sun into a sphere only 3 kilometers across, the resulting object would have an event horizon. Nothing, not even light, could escape from within that radius. For Earth, the Schwarzschild radius is approximately 9 millimeters. The Earth would need to be compressed to the size of a marble to become a black hole. The mathematical formula for the Schwarzschild radius is elegantly simple. It equals 2 times the gravitational constant multiplied by the mass, divided by the speed of light squared. This formula reveals a profound relationship between mass, gravity, and the ultimate cosmic speed limit. The more massive an object, the larger its Schwarzschild radius, and the easier it is for nature to create a black hole from it. A supermassive black hole with a mass of 6 billion suns has a Schwarzschild radius of approximately 18 billion kilometers, about the distance from the Sun to the outer edge of our solar system. The region inside the Schwarzschild radius, according to general relativity's predictions, is unlike anything else in physics. Based on what we can infer from the mathematics, the roles of space and time are interchanged. In normal space-time, you can move freely in any direction through space, but you are forced to move relentlessly forward through time. Inside a black hole, the situation appears to reverse. You would be forced to move toward the central singularity, just as inexorably as you are normally forced to move toward the future. The singularity is not a place in space, but a moment in time, your inevitable future once you cross the event horizon. The concept of a singularity at the center of a black hole is one of the most troubling aspects of the theory. A singularity is a point where the curvature of space-time becomes infinite, where the density of matter becomes infinite, where the known laws of physics break down. General relativity predicts the existence of singularities, but cannot describe what happens there. The theory points to its own incompleteness, indicating that a more fundamental theory, perhaps one that unifies gravity with quantum mechanics, is needed to understand what truly lies at the heart of a black hole. In 1935, Einstein and his colleague Nathan Rosen published a paper exploring another peculiar feature of the Schwarzschild solution. They discovered that the mathematics allowed for the existence of what they called a bridge connecting two distant regions of space-time. This Einstein-Rosen bridge, later popularized as a wormhole, suggested that black holes might connect to other regions of the universe, or even other universes entirely. While this remains highly speculative and has never been observed, it demonstrates how the mathematics of general relativity can lead to startling possibilities. For decades, most physicists, including Einstein himself, remained skeptical that black holes could actually form in nature. In 1939, Einstein published a paper arguing that black holes were impossible, claiming that the centrifugal forces from rotation would prevent any realistic object from collapsing to within its Schwarzschild radius. He missed the possibility that gravitational collapse could proceed so rapidly that these supporting forces would be overwhelmed. That same year, however, Robert Oppenheimer and his student Hartland Snyder published a paper that would prove prophetic. Solving Einstein's equations for an idealized collapsing star, they showed that if a star were massive enough, nothing could halt its gravitational contraction. The star would continue collapsing until it reached its Schwarzschild radius and beyond. To a distant observer, the collapse would appear to slow down as the star approached the event horizon, the light from its surface becoming increasingly redshifted and dimmed. Eventually, the star would appear to freeze at the event horizon, fading from view. But an observer falling with the star would notice nothing unusual as they crossed the horizon. They would simply continue falling, accelerating toward the central singularity. The true nature of the Schwarzschild radius was not understood until 1958, when David Finkelstein identified it as an event horizon, a perfect unidirectional membrane. Causal influences, including light, could cross the event horizon in only one direction, from outside to inside. Anything that crossed the horizon was irretrievably lost to the outside universe. Finkelstein's insight was crucial because it showed that the singularity at the Schwarzschild radius was not a physical singularity, not a place where the curvature of space-time became infinite, but rather a coordinate singularity, an artifact of the particular mathematical description Schwarzschild had used. By choosing different coordinates, the apparent singularity disappeared, revealing the event horizon as a perfectly smooth, if special, surface. The term black hole itself did not come into common use until the 1960s. The physicist John Wheeler, known for his creative nomenclature, is often credited with popularizing the term, though recent historical research suggests that an audience member at a 1967 lecture may have first used the phrase. Wheeler adopted it enthusiastically, and it quickly spread through the physics community and into popular culture. Before Wheeler, these objects were often called frozen stars or collapsed stars, names that did not capture the imagination nearly as effectively. Throughout the 1960s and 1970s, theoretical understanding of black holes advanced rapidly. Roger Penrose proved that singularities were not merely mathematical curiosities, but inevitable consequences of gravitational collapse in general relativity. If enough mass was concentrated in a small enough region, a singularity would form. This work, combined with Stephen Hawking's extensions showing that singularities were also unavoidable in the expansion of the universe, earned Penrose a share of the 2020 Nobel Prize in Physics. Hawking himself made perhaps the most surprising theoretical discovery about black holes. In 1974, he showed that when quantum mechanical effects were considered, black holes were not entirely black. According to his calculations, they would slowly emit radiation, now called Hawking radiation, gradually losing mass and eventually evaporating completely. While this phenomenon has not yet been directly observed due to the incredibly faint nature of the predicted emission, it remains one of the most significant theoretical predictions linking quantum mechanics and gravity. For stellar mass black holes, this process would take unimaginably long, far longer than the current age of the universe. For supermassive black holes, the evaporation time would be almost unfathomably long, extending to timescales that dwarf even the projected lifetime of all the stars in the universe. But the principle was profound. If the theory is correct, black holes are not eternal. They have temperatures, they have thermodynamic properties, and they would eventually disappear. By the time the Event Horizon Telescope project was conceived in the early 2000s, the theoretical framework was well established. General relativity predicted that a black hole, when backlit by hot, glowing gas, would cast a shadow. The boundary of this shadow would be approximately 2.6 times the Schwarzschild radius, corresponding to the closest stable orbit for light around the black hole. The shadow would be nearly circular, regardless of the black hole's spin, with any distortions too small to detect with current technology. The ring of emission surrounding the shadow would be brighter on one side than the other, a consequence of the Doppler effect as the material rotates at near light speeds. These predictions, derived from Einstein's equations over a century ago, would be tested by the Event Horizon Telescope. The image that emerged would either confirm the theory or reveal new physics beyond our current understanding. When the image was finally released, it matched the predictions with remarkable precision. The shadow was there, the ring was there, the asymmetric brightness was there. General relativity had passed yet another test, this time in the most extreme gravitational environment we have ever observed. Part 3. The Anatomy of Darkness. Before we can appreciate what the Event Horizon Telescope observed, we need to understand what black holes actually are, how they form, and what we expected to see when we finally pointed our Earth-sized telescope at one. The physics of black holes is as strange as any science fiction, and in many ways stranger, because it is real. Black holes come in several varieties, distinguished primarily by their mass. Stellar mass black holes, the smallest known type, form from the deaths of massive stars. When a star significantly more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. Throughout its life, a star exists in a delicate balance. The outward pressure from nuclear fusion reactions in its core exactly counteracts the inward pull of gravity from its enormous mass. When the fuel runs out, this balance is destroyed. For a star like our Sun, the end is relatively gentle. The core contracts until it reaches the density of a white dwarf, where electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, halts further collapse. The star sheds its outer layers as a planetary nebula and settles into a long twilight as a slowly cooling white dwarf. For more massive stars, the situation is far more violent. The core contracts past the white dwarf stage, crushing electrons and protons together to form neutrons. If the original star was not too massive, the collapse stops at this point, creating a neutron star, an object with the mass of the Sun compressed into a sphere only about 20 kilometers across. The density of a neutron star is almost inconceivable. A teaspoon of neutron star material would weigh billions of tons. But if the original star was massive enough, even neutron degeneracy pressure cannot halt the collapse. The core continues shrinking until it forms a black hole, typically with a mass between a few and a few dozen times the mass of our Sun. The gravitational wave observatories, LIGO and Virgo, have detected dozens of merging stellar mass black holes since their first detection in 2015, revealing a population of these objects that astronomers are still working to understand. At the other extreme are supermassive black holes, the cosmic giants that lurk at the centers of most large galaxies. These monsters contain millions to billions of times the mass of our Sun. The supermassive black hole at the center of our own Milky Way, known as Sagittarius A star, has a mass of approximately 4 million solar masses. The black hole at the center of Messier 87, the first to be imaged by the Event Horizon Telescope, is far larger still, containing approximately 6.5 billion solar masses. The formation of supermassive black holes presents one of the great puzzles in modern astrophysics. These objects exist in the centers of galaxies that are billions of light years away, which means we see them as they were billions of years ago, when the universe was young. Some of these distant black holes have masses of billions of solar masses, yet they existed when the universe was less than 1 billion years old. This poses a severe challenge. How did these black holes grow so massive so quickly? The simplest explanation would be that supermassive black holes grew from stellar mass seeds through accretion of surrounding gas. But there are physical limits to how fast a black hole can accrete matter. As gas falls toward a black hole, it heats up and radiates energy. This radiation exerts an outward pressure on the infalling gas, eventually balancing the inward pull of gravity. This balance point, called the Eddington limit, sets a maximum rate at which black holes can grow through normal accretion. If you calculate how long it would take a stellar mass black hole to grow to supermassive scales while respecting the Eddington limit, you find that it would take longer than the age of the universe. Yet we observe supermassive black holes in the early universe. Something does not add up. How supermassive black holes form remains one of the great unsolved problems in astrophysics. They appear to have existed even in the early universe, when there would not have been enough time for stellar mass black holes to grow to such enormous sizes through normal accretion. Several theories have been proposed. Perhaps the first stars, forming from pristine primordial gas, were far more massive than stars today and collapsed directly into intermediate mass black holes. Perhaps dense star clusters in the early universe provided environments where black holes could merge repeatedly, quickly building up to supermassive scales. Perhaps some other mechanism, yet to be discovered, allowed these cosmic behemoths to form. The question remains open. Between these extremes lies a possible intermediate class. Intermediate mass black holes, with masses ranging from hundreds to thousands of solar masses, have been hypothesized, but remain difficult to confirm observationally. Some globular clusters appear to harbor central black holes in this mass range, but the evidence is not yet definitive. The Event Horizon Telescope's observations of supermassive black holes provide one end of the mass spectrum. Gravitational wave detections of merging stellar mass black holes provide the other. intermediate mass black holes remain elusive. The structure of a black hole, at least as predicted by general relativity, is remarkably simple. A black hole has only three fundamental properties: mass, spin, and electric charge. This is known as the no-hair theorem, which states that any two black holes with the same mass, spin, and charge are completely identical, regardless of what material went into forming them. A black hole made from collapsing hydrogen is identical to one made from collapsing iron, provided they have the same mass, spin, and charge. All other information about the black hole's origin is lost, swallowed by the event horizon. In practice, astrophysical black holes are expected to have negligible electric charge. Any charged black hole would quickly attract oppositely charged particles from its surroundings, neutralizing itself. Thus, the black holes we observe are characterized almost entirely by their mass and spin. The mass determines the size of the event horizon. The spin, which can range from 0 to a theoretical maximum, affects the detailed shape of the spacetime around the black hole and the structure of any accretion disk. The event horizon itself is not a physical surface. You cannot touch it, and based on what general relativity tells us, nothing special would happen to you if you crossed it, at least not immediately. From your own perspective, crossing the event horizon of a sufficiently large black hole would likely be a non-event. Space-time would appear locally normal, and you would continue falling inward. Only later, as you approached the central singularity, would the tidal forces become extreme enough to cause problems. But from the perspective of an outside observer, something very different would appear to happen. As you fell toward the event horizon, the light you emitted would become increasingly redshifted, stretched to longer and longer wavelengths by the intense gravitational field. To the outside observer, your clock would appear to slow down, eventually appearing to freeze as you approached the horizon. You would never actually appear to cross the event horizon. Instead, your image would fade away, becoming dimmer and dimmer as the light you emitted became redshifted beyond the ability of any detector to see it. This gravitational time dilation and redshift are crucial to understanding what the event horizon telescope sees. The shadow of a black hole is not the event horizon itself, but rather the boundary inside which light cannot escape to reach us. This boundary is determined by the photon sphere, the closest distance at which light can orbit the black hole. For a non-rotating black hole, the photon sphere is located at 1.5 times the Schwarzschild radius. Photons at this distance can orbit the black hole indefinitely, though the orbit is unstable. Any perturbation will cause them to either spiral inward and be captured or spiral outward and escape. The shadow we observe is the projection of this capture region onto the sky. Light that approaches from behind the black hole can be bent around it and reach us, but light that enters the photon sphere from the wrong direction is captured. The resulting dark region, surrounded by the lensed and amplified light from behind and around the black hole, creates the characteristic shadow. For supermassive black holes like M87s, the shadow is surrounded by an accretion disk, a swirling vortex of superheated gas spiraling inward toward the event horizon. This material does not fall directly into the black hole. Instead, it spirals inward slowly, losing angular momentum through friction and magnetic turbulence. As it spirals, it heats up, reaching temperatures of billions of degrees in the innermost regions. This superheated plasma emits radiation across the electromagnetic spectrum, from radio waves to gamma rays. The physics of accretion disks is extraordinarily rich and complex. The basic picture is that gas captured by the black hole's gravity settles into a rotating disk, with material in the inner regions orbiting faster than material in the outer regions. This differential rotation creates friction between adjacent layers, heating the gas and causing it to slowly lose energy and spiral inward. The gravitational potential energy, released as the gas falls deeper into the black hole's gravitational well, is converted into heat and radiation. Near the innermost stable circular orbit, the disk becomes extremely hot and dense. This is the region that produces most of the high-energy emission observed from accreting black holes. For supermassive black holes with masses of billions of solar masses, the innermost stable orbit is located at about 3 times the Schwarzschild radius for a non-rotating black hole, or closer to the event horizon for a rapidly spinning black hole. The precise location depends on the black hole's spin. Beyond the innermost stable orbit, the accretion flow becomes more chaotic. Magnetic fields, amplified by the turbulent motion of the plasma, play a crucial role. These fields can tap the rotational energy of the black hole itself through a process called the Blanford-Znajek mechanism, extracting energy from the black hole's spin and using it to accelerate jets of plasma to nearly the speed of light. The temperature of the plasma near a supermassive black hole can exceed billions of degrees Kelvin. At such extreme temperatures, electrons are stripped from atoms, and the gas becomes a fully ionized plasma. The electrons in this plasma emit synchrotron radiation as they spiral through magnetic fields, producing the millimeter wavelength emission that the Event Horizon Telescope observes. The precise spectrum and structure of this emission depends on the density, temperature, and magnetic field configuration of the plasma, all of which are still being studied. The structure of the accretion disk and the surrounding environment determines what we see when we observe a black hole. The event horizon itself is invisible, but the glowing material around it illuminates the shadow, allowing us to perceive the dark heart of the beast. The Event Horizon Telescope observes at radio wavelengths, specifically at a wavelength of 1.3 millimeters, corresponding to a frequency of 230 gigahertz. At this wavelength, the emission from the hot gas near the black hole is bright enough to detect, while the atmosphere of Earth is still transparent enough to allow the observations. The choice of observing wavelength was not arbitrary. Shorter wavelengths would provide higher angular resolution, since the resolution of a telescope is inversely proportional to the wavelength of observation. But at shorter wavelengths, the Earth's atmosphere becomes increasingly opaque, absorbing and scattering the incoming radiation. Longer wavelengths would be easier to observe, but would sacrifice resolution. The 1.3 millimeter wavelength represents a compromise, providing sufficient resolution to image black hole shadows while remaining accessible to ground-based telescopes at the highest and driest sites on Earth. Additionally, many supermassive black holes, including M87s, produce powerful relativistic jets. These are beams of charged particles accelerated to nearly the speed of light, shooting outward from the poles of the black hole perpendicular to the accretion disk. The jet from M87's black hole extends thousands of light years into space, visible in images taken by the Hubble Space Telescope. The mechanism powering these jets is believed to involve the interaction of the black hole's spin with the magnetic fields in the accretion disk, a process known as the Blandford-Znajek mechanism. Based on theoretical models, this process could tap into the rotational energy of the black hole itself. The Event Horizon Telescope's observations are helping scientists understand how these incredible cosmic engines operate. When the Event Horizon Telescope collaboration planned their observations, they knew what to look for, based on decades of theoretical work and computer simulations. They expected to see a bright ring, the emission from the inner edge of the accretion disk, surrounding a dark central shadow. They expected the ring to be brighter on one side due to Doppler boosting, as the approaching side of the rotating disk would appear brighter than the receding side. They expected the shadow to be roughly circular, consistent with the predictions of general relativity. What they did not know was whether their observations would match these expectations or reveal something unexpected, something that might point to new physics beyond Einstein's theory. The image they eventually produced matched the predictions beautifully. The shadow was there, precisely the size predicted for a black hole of M87's mass. The ring was there, asymmetric in exactly the way expected from a rotating accretion disk. General relativity had passed its most stringent test yet. Part 4. The target, Messier 87's supermassive monster. When the Event Horizon Telescope collaboration chose their primary targets for the April 2017 observation campaign, they faced a careful balancing act. They needed black holes that were large enough and close enough to Earth that their event horizons would subtend a detectable angle on the sky. They needed targets that would be visible from multiple telescope sites simultaneously, essential for the interferometric technique to work. And they needed targets whose astrophysical conditions would produce enough emission at the observed wavelength to be detected. 2 targets met these criteria. Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, and M87 star, the supermassive black hole at the center of the giant elliptical galaxy, Messier 87. Both were observed during the 2017 campaign, but it was M87 star that produced the first successful image. Understanding why requires understanding what makes M87 special. Messier 87 is a giant elliptical galaxy located approximately 55 million light-years from Earth in the constellation Virgo. It was discovered in 1781 by the French astronomer Charles Messier, who catalogued it as the 87th entry in his famous list of nebulous objects that might be confused with comets. At the time, Messier had no idea what he was looking at. The true nature of M87 as an external galaxy, a separate island universe containing trillions of stars, would not be understood for another century and a half. The story of how astronomers came to understand galaxies is itself fascinating. Throughout the 19th century, observers cataloged thousands of fuzzy patches of light in the night sky, classifying them as nebulae. Some, like the Orion Nebula, were clearly clouds of glowing gas within our own Milky Way, but others, like M87, had a different character. They were more concentrated, more symmetrical, and showed no signs of the individual stars that made up the Milky Way's nebulae. The great debate about the nature of these spiral nebulae came to a head in 1920 when astronomers Harlow Shapley and Heber Curtis argued the question before the National Academy of Sciences. Shapley believed the spiral nebulae were relatively nearby objects, perhaps forming solar systems within our own galaxy. Curtis argued they were distant island universes, each comparable to our own Milky Way, but separated from us by vast stretches of empty space. The debate was settled in 1924 when Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, identified individual Cepheid variable stars in the Andromeda Nebula. These stars, whose intrinsic brightness could be determined from their pulsation period, allowed Hubble to calculate the distance to Andromeda. It was far too distant to be part of our own galaxy. The spiral nebulae were indeed external galaxies, and the universe was suddenly revealed to be incomprehensibly larger than anyone had imagined. M87 is enormous. It is one of the largest galaxies in the local universe, containing several trillion stars, roughly 10 times as many as the Milky Way. Unlike our disk-shaped spiral galaxy, M87 is an elliptical galaxy, a smooth, featureless ball of stars with no prominent spiral arms or dust lanes. Elliptical galaxies are generally older and more evolved than spiral galaxies, believed to form through the merger of multiple smaller galaxies over cosmic time. M87 shows evidence of such mergers in its diffuse stellar halo and its vast system of globular clusters, numbering approximately 12,000, far more than the roughly 200 globular clusters orbiting the Milky Way. The stellar population of M87 is predominantly old. Most of its stars formed more than 10 billion years ago, during a burst of star formation that accompanied the galaxy's initial assembly. Since then, star formation has largely ceased, leaving M87 populated by red giant stars and the remnants of more massive stars that have long since ended their lives. The galaxy glows with yellowish light, characteristic of old stellar populations, quite different from the blue tinge of young star-forming spiral galaxies. M87 sits at the center of the Virgo cluster, the nearest large cluster of galaxies to our own local group. The Virgo cluster contains approximately 2,000 galaxies of various sizes and types, all bound together by their mutual gravity. M87 is the dominant galaxy in this cluster, sitting at or near the center of the cluster's gravitational potential well. Its position makes it a natural gathering place for gas and smaller galaxies that fall into the cluster, likely contributing to its enormous size. At the center of M87 lurks one of the most massive black holes in the nearby universe. Early estimates of its mass varied widely, from 3.5 billion to over 6 billion solar masses, depending on the measurement technique used. The Event Horizon Telescope's observations provided a new independent measurement based on the size of the black hole's shadow. According to general relativity, the shadow size is directly proportional to the black hole's mass. By measuring the shadow and knowing the distance to M87, the collaboration determined the black hole's mass to be approximately 6.5 billion solar masses, with an uncertainty of only about 10%. To visualize this mass, consider that the black hole in M87 contains more mass than most dwarf galaxies. Its event horizon has a diameter of approximately 40 billion kilometers, roughly 270 astronomical units. more than 5 times the distance from the Sun to Pluto. If placed at the center of our solar system, the event horizon would extend well beyond the orbit of Neptune. The Schwarzschild radius alone is approximately 20 billion kilometers. One of the most striking features of M87 is its relativistic jet. First noticed in 1918 by the astronomer Heber Curtis, who described it as a curious straight ray extending from the galaxy's center. The jet is now known to be a beam of particles accelerated to nearly the speed of light by the intense magnetic fields near the black hole. The jet extends at least 5,000 light-years from the black hole, remaining visible across the electromagnetic spectrum from radio waves to X-rays. A counterjet, moving away from us on the opposite side of the black hole, is also present but appears much fainter due to relativistic beaming effects. The jet from M87's black hole has been studied extensively by radio telescopes and by the Hubble Space Telescope. Observations have revealed bright knots within the jet that appear to move faster than the speed of light, a phenomenon known as superluminal motion. This is not a violation of relativity, but rather an illusion caused by the jet moving at close to the speed of light, at a small angle to our line of sight. Material ejected toward us catches up to light emitted earlier, compressing the apparent travel time and making the motion appear faster than light. For the Event Horizon Telescope, M87's jet provided both a challenge and an opportunity. The jet originates from very close to the black hole, possibly within a few Schwarzschild radii of the event horizon. Understanding how the jet is launched is one of the key science goals of the EHT collaboration. Observations at the resolution of the event horizon could reveal where and how the jet connects to the black hole's accretion flow, potentially solving one of the longest-standing mysteries in astrophysics. Several factors made M87 star an ideal target for the Event Horizon Telescope's first image. First, despite being more than 1,000 times farther away than Sagittarius A star, M87's black hole is so much more massive that it subtends a similar angular size on the sky, approximately 40 to 50 micro-arcseconds. This meant the Event Horizon Telescope could potentially resolve both black holes with similar clarity. Second, M87 star is far more stable than Sagittarius A star. The gas around Sagittarius A star orbits the black hole in only a few minutes, causing the emission to vary rapidly. During an observation lasting several hours, the appearance of Sagittarius A star changes significantly, complicating the imaging process. The gas around M87's much larger black hole, in contrast, takes days to weeks to complete an orbit. During the observation window, M87 star remained essentially static, allowing the collaboration to treat it as a fixed target. Third, M87 is located at a celestial position visible to more of the Event Horizon Telescope's constituent sites simultaneously. While Sagittarius A star, located in the southern sky, can only be seen by a subset of the telescopes at any given time, M87 is better placed for observations with the full array. For all these reasons, M87 star was chosen as the primary target, and it was M87 star that appeared in the first image released to the world on April 10, 2019. The image showed a bright ring of emission, approximately 42 micro-arcseconds in diameter, surrounding a dark central region. The southern part of the ring was brighter than the northern part, consistent with emission from a rotating accretion disk with its southern edge approaching us and its northern edge receding. The size and shape of the ring matched the predictions of general relativity precisely. Subsequent analysis of the data revealed additional details. The magnetic field structure near the black hole could be inferred from polarization measurements, showing ordered fields that may play a crucial role in launching the jet. The brightness of the ring varied slightly between observation nights, suggesting rapid variability in the accretion flow. And the ring appeared consistent with a spinning black hole, though the exact spin could not be determined from the initial observations. In 2023, the collaboration released new images of M87 star created using a different algorithm called PRIMO, which produced sharper reconstructions from the same 2017 data. These images revealed finer details of the ring structure. Also in 2023, observations confirmed that M87's jet wobbles, precessing around an axis over a period of about 11 years. This precession is a direct consequence of the black hole's spin and provides the first direct observational evidence that M87 star is indeed a rotating Kerr black hole, not a static Schwarzschild black hole. M87 star has become one of the most studied objects in modern astrophysics, and the Event Horizon Telescope's observations have opened an entirely new window onto its nature, but it was not the only target. The collaboration also observed Sagittarius A star, the black hole at the heart of our own galaxy, and that image would come 3 years later. Part 5, Our Own Galactic Heart, Sagittarius A star. While M87 star made headlines as the first black hole to be imaged, the Event Horizon Telescope had another target in its sights that was, in many ways, even more significant. Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, sits only about 26,000 light-years from Earth. It is our nearest supermassive black hole, the gravitational anchor around which our entire galaxy revolves. The history of Sagittarius A star's discovery stretches back decades before the Event Horizon Telescope. Beginning in 1931, radio engineer Carl Jansky, working at Bell Telephone Laboratories in New Jersey, detected a persistent hiss of radio interference while investigating sources of static affecting transatlantic phone communications. After more than a year of careful study, he determined that this mysterious signal repeated on a 23-hour, 56-minute cycle, matching the sidereal day rather than the solar day. This meant the source was not terrestrial, but cosmic. In 1933, Jansky announced his revolutionary finding. The radio waves were emanating from the direction of the constellation Sagittarius toward the center of the Milky Way. Jansky did not have the resolution to pinpoint the source precisely, but his observations marked the birth of radio astronomy and the first detection of radio emission from the galactic center. In 1974, astronomers Bruce Ballack and Robert Brown used the Green Bank interferometer to study the galactic center region with much higher resolution. They discovered an exceptionally bright, compact radio source that appeared to be at the exact center of the galaxy. Brown named this source Sagittarius A star in 1982, using the asterisk notation typically reserved for excited atomic states to indicate its special nature. The source was embedded within a larger, more diffuse radio region called Sagittarius A. Over the following decades, astronomers accumulated evidence that Sagittarius A star was not an ordinary radio source, but something far more exotic. Very long baseline interferometry observations revealed that the source was extremely compact, smaller than a few astronomical units. Whatever was producing the radio emission had to be confined to a region smaller than our solar system. The breakthrough came from observations at infrared wavelengths, which can penetrate the dense dust, clouds obscuring the galactic center from visible light. Beginning in the early 1990s, two teams of astronomers embarked on decades-long campaigns to track the orbits of stars very close to Sagittarius A star. One team, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, observed from the European Southern Observatory in Chile. The other team, led by Andrea Ghez at UCLA, observed from the Keck Observatory in Hawaii. Both teams discovered stars moving at tremendous speeds near the galactic center. One star, designated S2, completes an orbit around Sagittarius A star in only about 16 years, swooping to within 17 light hours of the invisible object at closest approach. At that distance, S2 accelerates to approximately 7,650 kilometers per second, close to 3% of the speed of light. The only object that could produce the gravitational influence necessary to maintain such an orbit, while remaining invisible at all wavelengths, was a supermassive black hole. By carefully tracking the orbits of S2 and other stars over more than 2 decades, both teams independently determined the mass of Sagittarius A star. The current best estimate is approximately 4 million solar masses, with an uncertainty of only a small fraction of a percent. For their discovery that Sagittarius A star is a supermassive compact object for which a black hole is the only plausible explanation, Reinhard Genzel and Andrea Ghez were awarded half of the 2020 Nobel Prize in Physics. The other half went to Roger Penrose for his theoretical work, showing that black holes are a robust prediction of general relativity. Compared to M87's monster, Sagittarius A star is relatively modest. Its mass is more than 1,000 times smaller than M87 stars. Its event horizon is correspondingly smaller, with a Schwarzschild radius of only about 12 million kilometers, roughly 17 times the radius of the Sun. But because it is so much closer to us, Sagittarius A star subtends almost exactly the same angular size on the sky as M87 star, approximately 50 microarcseconds. Both black holes were viable targets for the Event Horizon Telescope. Imaging Sagittarius A star, however, proved far more challenging than imaging M87 star. The primary reason is the difference in variability. The timescale for changes in the appearance of an accreting black hole is roughly proportional to its mass. For M87 star, with its billions of solar masses, the innermost stable orbit has a period of several days to weeks. For Sagittarius A star, with its millions of solar masses, the innermost stable orbit has a period of only about half an hour. This rapid variability meant that Sagittarius A star's appearance changed significantly during the several-hour observation periods of the Event Horizon Telescope. The gas around the black hole was not stationary. It was swirling, flaring, evolving, even as the telescopes watched. Creating a coherent image from such dynamic data required developing entirely new techniques, methods that could account for the source's variability rather than assuming it was static. The collaboration divided into teams and developed sophisticated new analysis methods. They simulated millions of possible images, comparing the simulated data to the actual observations to determine which images were consistent with what the telescope had detected. They averaged over the variability, producing a composite image that represented the typical appearance of Sagittarius A star during the observation period. 3 years after the M87 star image was released on May 12, 2022, the Event Horizon Telescope collaboration announced that they had successfully imaged Sagittarius A star. The image showed a bright ring of emission surrounding a dark central shadow, just as they had seen for M87 star. The ring had a diameter consistent with the predicted shadow size for a black hole of 4 million solar masses. The overall structure was remarkably similar to M87 star, despite the 1,000-fold difference in mass and the very different host galaxies. This similarity was itself a profound result. It confirmed that general relativity governs black hole physics across an enormous range of masses and environments. A black hole in a giant elliptical galaxy 55 million light-years away looks almost identical to a black hole in our own spiral galaxy, just as Einstein's theory predicted. Any differences we see at larger scales must be due to the different environments and accretion flows, not to differences in the fundamental nature of the black holes themselves. The Sagittarius A star image showed a few intriguing differences from M87 star. The brightness distribution around the ring was different, with the brightest regions shifting to different positions in different analysis runs. This was expected given the source's variability. The image represented a time-average view of a constantly changing system. Future observations with improved techniques may allow scientists to create movies of the gas swirling around Sagittarius A star, capturing its dynamics in real time. Observations of Sagittarius A star continue to reveal surprises. Recent data from the XRISM X-ray satellite has shown evidence that the black hole was more active in the past, with X-ray echoes suggesting powerful flares occurring over the last 1,000 years. Based on this evidence, astronomers believe the black hole that appears so quiet today may have been far more dramatic in the relatively recent cosmic past. Part 6. Building the Earth-sized telescope. The Event Horizon Telescope is not a single instrument. It is a global collaboration of radio observatories, united by sophisticated technology and a shared scientific vision. Understanding how this Earth-sized virtual telescope was assembled requires understanding the technique that makes it possible. Very long baseline interferometry. The fundamental principle of interferometry is that waves from the same source, arriving at two different detectors, will interfere with each other. If the waves arrive in phase, they constructively interfere, producing a stronger combined signal. If they arrive out of phase, they destructively interfere, partially or completely canceling each other out. By measuring how the interference pattern changes as the orientation and separation of the detectors varies, astronomers can extract information about the spatial structure of the source. This principle has been understood since the early 19th century, when Thomas Young demonstrated the interference of light waves in his famous double-slit experiment. The application of interferometry to astronomy began in the late 19th century with the Michelson stellar interferometer, which was used to measure the diameters of nearby stars. by observing how the interference pattern changed as the separation between two small mirrors was varied. Astronomers could determine the angular size of stars too small to resolve with any conventional telescope. For optical and infrared telescopes, interferometry typically requires physically connecting the instruments with mirrors or optical fibers, ensuring that the light from each telescope arrives at a common detector with its phase information preserved. This limits the separation between telescopes to at most a few hundred meters. Building longer optical baselines requires heroic engineering to maintain the path lengths to within a fraction of a wavelength of light. Radio waves, however, have much longer wavelengths, and their phase can be recorded electronically rather than optically. This allows radio astronomers to record observations at widely separated sites, then combine the data later at a central processing facility. The key insight is that if you know precisely when each telescope recorded its data, you can align the recordings in post-processing, effectively recreating the interference pattern that would have been observed if the telescopes had been physically connected. This is the essence of very long baseline interferometry, or VLBI. Each telescope in the network records the incoming radio waves, along with precise timing signals from an atomic clock, typically a hydrogen maser, with stability measured in parts per quadrillion. These hydrogen masers are extraordinary devices, maintaining their frequency with such precision that they would drift by only 1 second over millions of years. This precision is necessary because the interference pattern depends on knowing the relative timing of observations to within a fraction of a wavelength, which, at the Event Horizon telescopes, observing frequency corresponds to a few picoseconds or trillionths of a second. The recordings from all telescopes are then shipped to a central facility where a specialized supercomputer called a correlator combines them, searching for the interference patterns that reveal the structure of the observed source. The correlator must try billions of different relative delays between the telescope signals, searching for the combinations that produce correlated signals. When correlation is found, it indicates that both telescopes were detecting emission from the same region of the source, and the strength and phase of the correlation encode information about the source structure. The resolution of a VLBI network is determined by the longest baseline, the greatest separation between any two telescopes in the array. The relationship is straightforward. The angular resolution equals the observing wavelength divided by the baseline length. For the Event Horizon telescope, with telescopes spanning from Hawaii to Spain and from the South Pole to Arizona, baselines extend to nearly the diameter of the Earth, approximately 12,000 kilometers. This gives the EHT an angular resolution of about 20 microarcs seconds at its observing wavelength of 1.3 millimeters, sufficient to resolve the shadow of a supermassive black hole. To appreciate how astonishing this resolution is, consider that 20 microarcseconds is approximately the angular size of a tennis ball on the surface of the Moon as seen from Earth. It is the resolution required to read the date on a quarter from a distance of more than 100 miles. No other observational technique in astronomy, at any wavelength, achieves angular resolution comparable to what VLBI provides at millimeter wavelengths. The Event Horizon Telescope project evolved over many years, building on decades of development in millimeter wavelength, VLBI. Key technical advances included the development of high-bandwidth recording systems capable of capturing data at rates of tens of gigabits per second, and the deployment of hydrogen master clocks at all participating sites to ensure the necessary timing precision. For the April 2017 observation campaign, the historic campaign that produced the first black hole image, 8 telescope facilities at 6 geographic locations participated. These were the Atacama Large Millimeter Array and the Atacama Pathfinder experiment in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell Telescope, and the Submillimeter Array in Hawaii, the Large Millimeter Telescope Alfonso Serrano in Mexico, the Submillimeter Telescope in Arizona, and the South Pole Telescope in Antarctica. Each of these facilities brought unique capabilities to the network. The Atacama Large Millimeter Array, or ALMA, is by far the most sensitive millimeter wavelength telescope in the world, consisting of 66 individual antennas that can be combined into a single-phased array. ALMA provided the anchor point for the Event Horizon Telescope, dramatically increasing the sensitivity of baselines to other sites. Without ALMA, the Event Horizon Telescope would not have achieved the sensitivity necessary to detect the faint emission from M87's black hole. The South Pole Telescope, located at the Amundsen-Scott South Pole Station, provided the longest north-south baselines in the array. However, the extreme isolation of the South Pole meant that data recorded there could not be shipped out until the end of the Antarctic winter. The hard drives from the 2017 April observations did not arrive at the processing centers until December, delaying the analysis significantly. Coordinating observations across such a diverse array of facilities was an enormous logistical challenge. Observations had to be scheduled for times when the target was visible from all or most sites, when weather conditions were favorable at all locations, and when all telescopes were available. The millimeter wavelengths at which the EHT observes are strongly absorbed by water vapor in the atmosphere, so observations require exceptionally dry conditions. Most EHT sites are located at high altitudes or in polar regions, specifically to minimize atmospheric interference. During the observation period, a central command room at the Smithsonian Astrophysical Observatory coordinated activities across the network. Weather forecasts were monitored continuously, and observation decisions were made daily based on conditions at all sites. The team had a 10-day window and aimed to observe on as many nights as conditions permitted. In the end, they achieved 5 nights of observations, collecting approximately 3.5 petabytes of data. Once the observations were complete, the data had to be shipped physically to the processing centers. The volume of data was simply too large to transmit over the internet in any reasonable time. Hard drives were packed into shipping containers and sent by air freight to the Max Planck Institute for Radio Astronomy in Bonn, Germany, and to the MIT Haystack Observatory in Massachusetts. There, the correlators combined the signals from all the telescopes, a process that required months of computation. Even after correlation, the data required extensive calibration and analysis before images could be produced. Atmospheric fluctuations, instrumental effects, and various sources of noise had to be identified and corrected. Multiple teams worked independently to perform this calibration, comparing their results to ensure consistency. Only when all teams agreed that the data had been properly processed could the imaging phase begin? The imaging itself was another major challenge. The Event Horizon Telescope does not produce images directly. Instead, it measures visibilities, the interference between pairs of telescopes at different separations and orientations. These visibilities contain information about the Fourier transform of the source brightness distribution. Recovering the original image from the measured visibilities is an inverse problem, and because the EHT has only a sparse array of telescopes, the visibilities sample only a small fraction of the full Fourier plane. There are infinitely many images that would be consistent with the measured data. To select a single best image, imaging algorithms must make assumptions about what realistic astronomical sources look like. Traditional algorithms like CLEAN, developed in the 1970s, assume that sources consist of collections of point sources. More modern techniques, like the CHIRP algorithm developed by Katie Booman and colleagues, use statistical models of natural images to constrain the reconstruction. The Event Horizon Telescope collaboration used multiple independent algorithms run by separate teams to ensure that the final image was robust against the choice of method. Since the initial observations in 2017, the Event Horizon Telescope has continued to expand. Additional telescopes have joined the network, including the Greenland Telescope, the Noema Array in France, and the Kitt Peak 12-meter telescope in Arizona. These new sites improve the coverage of the Fourier plane, enabling sharper and more reliable images. Future observation campaigns promise to reveal ever more detail about the black holes at the centers of M87 and the Milky Way. Part 7. The Observation Campaign of April 2017. The week of April 5th through 11th, 2017, marked the culmination of more than a decade of preparation. Across the globe, teams of astronomers gathered at radio observatories, checking and rechecking their equipment, monitoring weather forecasts, and preparing for the most ambitious observation campaign in the history of radio astronomy. For the first time, the full Event Horizon Telescope Array, including the transformative addition of the Atacama Large Millimeter Array, would be pointed at the supermassive black holes in M87 and the Milky Way. The observation window had been carefully chosen. The targets had to be visible from multiple sites simultaneously. The weather had to be favorable at all locations, and the full moon had to be avoided to minimize background noise in some detectors. The 10-day window from April 5th to April 14th satisfied these constraints, providing the best opportunity for observations. Each day began with a weather assessment. The millimeter wavelengths at which the Event Horizon Telescope observes are strongly affected by atmospheric water vapor, which absorbs and scatters the incoming radiation. Even thin clouds or high humidity can significantly degrade the data quality. Forecasts were gathered from all participating sites and analyzed at the Central Coordinating Center at the Smithsonian Astrophysical Observatory. On good nights, when conditions were favorable at most sites, the order went out to observe. Teams at each telescope sprang into action, positioning their dishes, verifying the synchronization of their atomic clocks, and beginning the recording of data. The observations typically lasted for several hours, tracking the targets as they moved across the sky. The first night of observations, April 5th, focused on calibration sources and the supermassive black whole Sagittarius A star. Conditions were good at most sites, and the data recorded that night showed strong signals, confirming that the array was working as planned. The following nights continued with observations of both Sagittarius A star and the primary target, M87's black hole. Weather conditions varied throughout the campaign. Some nights were excellent, with crystal clear skies at all sites. Other nights required difficult decisions as conditions deteriorated at one or more locations while remaining favorable elsewhere. The team had to balance the desire for complete data sets against the risk of recording poor quality data that would be difficult to calibrate. In total, the collaboration achieved 5 nights of good observations during the 10-day window. This was an excellent outcome, better than the minimum needed for a successful campaign. The data recorded on those 5 nights would take years to fully analyze, ultimately producing the historic first image of a black hole. At each telescope, the incoming radio waves were converted to electronic signals, amplified, and digitized at rates of tens of gigabits per second. These digital signals were recorded on high-capacity hard drives, along with timing signals from the hydrogen maser atomic clocks that kept all the observations synchronized to within fractions of a trillionth of a second. The volume of data was staggering. Each telescope produced roughly 350 terabytes of data per day of observation. Across the entire array and all observation nights, the total exceeded 3.5 petabytes, equivalent to roughly 350 million high-resolution photographs. This data was stored on thousands of hard drives, which were then packaged for shipment to the processing centers. For most sites, the hard drives could be shipped immediately after the observations concluded. But the South Pole Telescope presented a unique challenge. The South Pole is inaccessible for much of the year, with no flights in or out during the Antarctic winter from approximately April through October. The hard drives recorded at the South Pole in April 2017 could not be shipped until the station reopened in late November. They arrived at the processing centers in December, nearly 8 months after the observations were made. While waiting for the South Pole data, the correlation of data from other sites proceeded. The correlators at the Max Planck Institute and MIT Haystack Observatory combined signals from pairs of telescopes, searching for the characteristic interference patterns that indicated successful detection of the source. Preliminary results were encouraging, showing strong signals on multiple baselines, but the full analysis had to wait until all data was available. Once the South Pole data arrived, the processing accelerated. Over the following months, the correlation was completed, and teams began the laborious process of calibration. Atmospheric effects had to be removed, instrumental delays had to be corrected, and the data had to be converted into a form suitable for imaging. Each step required careful verification, with multiple teams working independently to cross-check results. By early 2018, the calibrated data was ready for imaging, but the collaboration took an unusual step to ensure the robustness of their results. Rather than having a single team produce the final image, they divided into 4 independent groups, each using different imaging software and techniques. The groups were instructed not to communicate about their results until they had each produced their best image. This blind imaging approach was designed to prevent any single person's biases or expectations from influencing the outcome. If all four groups working independently with different methods arrived at the same basic image structure, that would be strong evidence that the image was real and not an artifact of any particular algorithm. In the summer of 2018, the four groups came together to compare their results. The tension in the room was palpable. Months of work had led to this moment. One by one, the teams revealed their images, and one by one, they showed the same basic structure: a bright ring of emission surrounding a dark central shadow, brighter on the southern side than the northern. The agreement was not perfect in all details. Different algorithms produced slightly different fine-scale features, as expected given the sparse data coverage. But the fundamental structure was consistent across all reconstructions. The dark shadow was real. The bright ring was real. The Event Horizon Telescope had succeeded in imaging a black hole, but the announcement would have to wait. The collaboration spent another year performing additional analyses, checking for systematic errors, and preparing scientific papers describing the results. They wanted to be absolutely certain before going public. In April 2019, exactly 2 years after the observations were made, the Event Horizon Telescope collaboration held simultaneous press conferences around the world to reveal the first image of a black hole to an astonished public. Part 8. From petabytes to pixels. The data processing. The journey from raw telescope data to the iconic image of M87's black hole was one of the most complex data processing efforts ever undertaken in astronomy. It required years of work by hundreds of scientists, the development of new algorithms and techniques, and computational resources that pushed the limits of available technology. Understanding this process reveals just how difficult it is to image something as small and distant as a black hole's shadow. The first step in the process was correlation, combining the signals from different telescopes to detect the interference patterns that encode information about the source. This is the heart of very long baseline interferometry, the technique that allows widely separated radio telescopes to function as a single virtual dome instrument. When a radio wave from M87 reaches Earth, it arrives at different telescopes at slightly different times, depending on the geometry of the array and the direction to the source. These time delays are typically measured in nanoseconds, corresponding to path differences of a few meters. By precisely accounting for these delays and combining the signals, the correlator reveals how the signals from different telescopes interfere with each other. The interference pattern depends on the spatial structure of the source. A point source produces a simple pattern, while an extended source with complex structure produces a more complicated pattern. By measuring the interference on many different baselines, each corresponding to a different pair of telescopes, astronomers can build up information about the source structure across a range of spatial scales. The Event Horizon Telescope's correlators, located at the Max Planck Institute for Radio Astronomy in Bonn and at MIT Haystack Observatory, are specialized supercomputers designed specifically for this task. They process the data from all the telescopes simultaneously, searching for correlated signals at millions of different delay values. The processing required for the 2017 data took months to complete. After correlation, the data consists of a set of complex numbers called visibilities, each corresponding to a particular baseline at a particular time. The amplitude of each visibility indicates the strength of the correlated signal, while the phase indicates the relative timing. Together, the visibilities encode all the information about the source structure that the telescope array can measure. But the visibilities are not an image. Converting them into an image requires inverting the relationship between the source brightness distribution and the measured visibilities. This relationship is a Fourier transform. The visibilities are samples of the Fourier transform of the source, brightness at spatial frequencies determined by the baseline lengths and orientations. If the Event Horizon Telescope had infinitely many telescopes densely covering the Earth, it would sample the Fourier transform at all spatial frequencies, and the inverse transform would directly yield the source image. In reality, the array has only 8 telescopes, providing a sparse sampling of the Fourier plane. Many spatial frequencies are not measured at all. This means there are infinitely many images that would be consistent with the measured data. To produce a single image, imaging algorithms must choose among these possibilities based on additional constraints or assumptions. The traditional approach, called clean, assumes the source can be represented as a collection of point sources. It iteratively identifies the brightest point in a preliminary image, subtracts its contribution from the data, and repeats until the residual noise level is reached. The final image is then smoothed to produce a continuous brightness distribution. More modern techniques use different assumptions. Regularized maximum likelihood methods, developed by several groups including Katie Bouman and her colleagues, incorporate statistical models of what realistic images should look like. These methods search for images that fit the data well, while also satisfying constraints like smoothness, sparsity, or similarity to training images. Bouman's algorithm, called CHIRP, for continuous high-resolution image reconstruction using patch priors, was particularly influential in the development of EHT imaging techniques. CHIRP uses machine learning trained on natural images to identify statistical regularities that can guide the reconstruction. It also incorporates a clever trick to handle atmospheric phase errors by using closure phases, combinations of 3 baselines whose individual phase errors cancel out. The algorithm becomes robust against the atmospheric fluctuations that plague millimeter wavelength observations. However, it is important to note that the final M87 image was not produced by any single algorithm. Instead, the collaboration used multiple methods and compared the results. 4 independent imaging teams, each using different software and techniques, produced images without consulting each other. Only after all teams had completed their work did they compare results. The agreement between the independent reconstructions was remarkable. All 4 teams produced images showing a ring-like structure approximately 40 micro-arcseconds in diameter, with a dark central region and brighter emission on the southern side, while the detailed structure within the ring varied between reconstructions. The fundamental features were consistent. This convergence provided strong evidence that the observed structure was real, not an artifact of any particular imaging algorithm. It is one of the key reasons the scientific community accepts the EHT results as robust. The black hole shadow is not something that any single team invented or imagined into existence. It emerged independently from multiple analyses using entirely different methods. Beyond imaging, The collaboration performed extensive additional analyses to characterize the black hole and its environment. They measured the mass of the black hole from the shadow size, finding 6.5 billion solar masses, consistent with previous estimates from stellar dynamics. They searched for variability between observation nights, finding subtle changes in the brightness distribution. They analyzed the polarization of the emission, revealing information about the magnetic field structure near the black hole. All of these analyses required careful calibration to remove systematic errors. Atmospheric fluctuations, which can change on timescales of seconds, had to be tracked and removed. Instrumental effects, such as amplitude and phase variations within each telescope, had to be characterized and corrected. The data from each telescope had to be placed on a common flux scale, accounting for differences in sensitivity and calibration. The calibration process itself took many months. Multiple teams worked in parallel, developing independent calibration pipelines and comparing results. Discrepancies were investigated and resolved. Only after all teams agreed that the data had been properly calibrated could the imaging proceed. From start to finish, the journey from observation to final image took approximately 2 years. The observations were made in April 2017. The correlation was completed by mid-2018. The imaging and analysis continued through the end of 2018 and into 2019. The results were published and announced to the public in April 2019. Throughout this period, hundreds of scientists worked to ensure that the final image was as accurate and reliable as possible. Part 9. The Revelation. April 10th, 2019, and beyond. The morning of April 10th, 2019, was like no other in the history of astronomy. In 6 cities across 4 continents, scientists gathered for simultaneous press conferences. In Brussels, Washington, Santiago, Shanghai, Tokyo, and Taipei, screens displayed identical images, and speakers in multiple languages described identical results. After more than a century of theoretical prediction and decades of technological development, humanity was about to see a black hole for the first time. When the image appeared on screens around the world, it was immediately recognizable. A bright ring of orange light, glowing against the darkness of space, surrounded a region of profound shadow. The southern part of the ring was noticeably brighter than the northern part. This was not an artist's conception or a computer simulation. This was real data, real photons that had traveled 55 million light years from the heart of the galaxy Messier 87 to reach telescopes on Earth. The reaction was immediate and overwhelming. The image appeared on the front pages of newspapers worldwide. It trended on social media for days. Scientists who had worked on the project for years became overnight celebrities. Katie Bouman, whose algorithms had helped make the image possible, saw her photograph, capturing her moment of joy as the first image appeared on her computer screen, go viral around the world. That image, showing Bouman hunched over her laptop, with her hands pressed to her face in a gesture of astonished delight, became almost as iconic as the black hole image itself. The public fascination with the black hole image was extraordinary. Within hours of the announcement, it had been viewed by hundreds of millions of people. News organizations around the world devoted extensive coverage to explaining what the image showed and why it mattered. Children in schools learned about black holes. Artists created renderings and interpretations. The image appeared on t-shirts, coffee mugs, and countless internet memes. Part of this fascination stemmed from the sheer visual impact of the image. Here was something that had existed only in equations and computer simulations, something that many people had assumed would forever remain invisible, and now it was right there on their screens. The bright ring against the darkness, with its subtle asymmetry and central shadow, had an almost mystical quality. It looked like an eye, some observers noted, as if the universe were gazing back at us. But the public reaction also reflected a deeper hunger for discovery, a recognition that humanity had accomplished something truly remarkable. In an era often dominated by divisive news and pessimistic predictions, the black hole image offered something different, a story of global cooperation, patient research, and the triumph of human curiosity. More than 200 scientists from around the world had worked together for years to achieve this result, overcoming technical challenges that would have seemed insurmountable only decades earlier. But beyond the public excitement, the scientific significance of the image was profound. For the first time, we had direct visual evidence of an event horizon, the point of no return around a black hole. The size and shape of the shadow matched the predictions of general relativity with remarkable precision. Einstein's theory, formulated over a century earlier, had passed its most stringent test yet. The collaboration published their results in a series of 6 papers in a special issue of the Astrophysical Journal Letters. These papers described the observations, the data processing, the imaging techniques, and the physical interpretation of the results. Together, they represented one of the most complete and careful presentations of an astronomical discovery ever published. The mass of M87's black hole, derived from the shadow size, was determined to be approximately 6.5 billion solar masses. This was consistent with previous estimates from stellar dynamics and gas kinematics, providing independent confirmation of those measurements. The diameter of the shadow was approximately 42 microarcseconds, corresponding to a physical size of about 40 billion kilometers. The brightness asymmetry of the ring provided information about the orientation and rotation of the accretion disk. The brighter southern region indicated that the emission was Doppler boosted, approaching us at a significant fraction of the speed of light. Combined with the known orientation of M87's jet, this allowed scientists to infer the rotation direction of the black hole itself. In the years following the initial image, the Event Horizon Telescope collaboration continued to analyze the 2017 data and conduct new observations. In March 2021, they released images of M87 in polarized light, revealing the structure of the magnetic field near the black hole. The polarization pattern showed ordered magnetic fields spiraling around the black hole, consistent with theoretical models of how relativistic jets are launched. In May 2022, the collaboration announced the image that had been awaited since the beginning, the first image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Despite being more than 1,000 times smaller than M87's black hole, Sagittarius A star produced an image with a remarkably similar structure. A bright ring surrounded a dark shadow, approximately the size predicted by general relativity. The similarity between the two images despite the enormous difference in black hole mass and host galaxy environment, was itself a scientific result. It confirmed that general relativity governs black hole physics across a vast range of scales. A 4 million solar mass black hole in a spiral galaxy looks essentially the same as a 6.5 billion solar mass black hole in a giant elliptical, just as Einstein's equations predict. In 2023, the collaboration released new images of M87 created using the PRIMO algorithm, which produced sharper reconstructions from the same 2017 data. These images revealed finer details in the ring structure, including a thin, bright ring that may be related to the photon ring predicted by general relativity, though this interpretation remains a matter of ongoing scientific discussion. Also in 2023, observations confirmed that M87's black hole is spinning. By tracking the orientation of the relativistic jet over more than 2 decades, astronomers found that it wobbles, precessing around an axis over an 11-year period. This precession is a direct consequence of the interaction between the black hole's spin and the surrounding accretion disk. For the first time, we had direct evidence that M87's black hole is a rotating Kerr black hole, not a static Schwarzschild black hole. The Event Horizon Telescope continues to observe both M87 and Sagittarius A star, along with other targets, including the cores of nearby active galaxies. Each observation campaign adds more data, allowing for better images and new scientific insights. The collaboration has grown to include more than 300 scientists at more than 80 institutions in more than 20 countries. The impact of the first black hole image extended far beyond the scientific community. It captured the public imagination in a way few astronomical discoveries have. For the first time, the abstract concept of a black hole became something tangible, something you could actually see. The image has been reproduced millions of times, appearing on everything from science textbooks to coffee mugs. It has become an icon of human achievement, a symbol of what we can accomplish when we combine our intellect, our technology, and our global cooperation. Part 10, The Future of Black Hole. Imaging. The first images of M87 and Sagittarius A star were just the beginning. The Event Horizon Telescope collaboration is already planning the next generation of observations, which promise to reveal even more about these cosmic monsters. Within the coming decade, we may see the first movies of black holes, watching as gas swirls around the event horizon in real time. The Next Generation Event Horizon Telescope, or NGEHT, is a planned expansion of the current array that will approximately double the number of participating telescopes. The National Science Foundation has awarded a $12.7 million grant to design and develop this enhanced network. Led by Shepard Dolman, the founding director of the Event Horizon Telescope, the NGEHT team is designing new antenna dishes, new receiver systems, and new imaging algorithms that will dramatically improve the capabilities of black hole imaging. The design of the NGEHT involves carefully choosing locations for new telescope stations. The goal is to fill in gaps in the current array's coverage of the Fourier plane, providing more complete information about the source structure. Ideal locations are at high altitude, where atmospheric water vapor is minimized and distributed geographically to provide baselines at a variety of lengths and orientations. Potential sites include locations in Africa, which is currently underrepresented in the array, as well as additional stations in South America and Asia. The new dishes being designed for the NGEHT represent a significant advance over existing telescopes in the array. They will be optimized specifically for millimeter wavelength (VLBI) with high surface accuracy and efficient receivers. The design process involves trade-offs between dish size, which determines sensitivity, and cost, which constrains the number of stations that can be built. A consortium of engineers and astronomers is working to find the optimal balance. In August 2023, the Smithsonian Astrophysical Observatory selected a contractor, MTEX Technology, GmbH of Germany, to design and build the new antennas for the NGEHT. This marked a major milestone in the project's development, moving from conceptual design to actual hardware construction. The new antennas are expected to be deployed by the end of this decade. The key goals of the NGEHT are to increase the number of telescopes in the array, to add observations at additional radio frequencies, and to develop faster data transfer systems that allow near real-time correlation. Together, these improvements will fill in the gaps in the current array's coverage of the Fourier plane, enabling sharper images with higher dynamic range. The addition of multiple observing frequencies is particularly important. The current EHT observes at a single frequency of 230 GHz. The NGEHT will add observations at 86 GHz and 345 GHz, providing information at multiple wavelengths simultaneously. Different frequencies probe different physical processes in the plasma near the black hole, and combining multi-frequency data can help disentangle the effects of optical depth, temperature, and magnetic field structure. The development of faster data transfer protocols addresses one of the current limitations of VLBI. Currently, data must be physically shipped on hard drives from each telescope to the processing centers, a process that can take months for remote locations like the South Pole. The NGEHT aims to develop high bandwidth connections that would allow data to be transferred electronically in near real time. This would dramatically speed up the analysis process and could eventually enable live monitoring of black hole activity. With its enhanced capabilities, the NGEHT will be able to produce movies of black holes for the first time. The gas around Sagittarius A star completes an orbit in about 30 minutes, changing the appearance of the emission significantly over the course of a night. The current Event Horizon Telescope produces time-averaged images that blur out this variability. The NGEHT, with its faster imaging speed and better coverage, will be able to track these changes, producing frame-by-frame images that can be assembled into movies showing the dynamics of accretion. Such movies would be scientifically transformative. They would allow astronomers to directly observe the plasma orbiting the black hole, measuring its velocity and studying its turbulence. Based on theoretical predictions, they could reveal how magnetic fields near the event horizon evolve, potentially capturing the launching of relativistic jets. They would provide the most direct test yet of general relativity in strong gravitational fields, assuming our current theoretical framework is correct. Beyond movies, the NGEHT will enable observations of more distant black holes. The current array can only image the very nearest supermassive black holes, those whose shadows subtend angles of at least a few tens of microarcseconds. With improved sensitivity and resolution, the NGEHT may be able to detect and resolve black holes in more distant galaxies, allowing statistical studies of black hole properties across a range of masses and environments. The NGEHT will also enable more detailed studies of the known targets. For M87, higher resolution images may reveal the connection between the black hole and its relativistic jet, showing how the jet is launched from the inner accretion flow. For Sagittarius A star, better coverage may allow the disentanglement of the rapid variability, revealing the underlying structure that is currently blurred by time averaging. Looking further into the future, some scientists are contemplating even more ambitious projects. The Black Hole Explorer, or BHEX, is a proposed space-based radio telescope that would extend the baselines of the Event Horizon Telescope beyond the diameter of the Earth. By placing a telescope in space, potentially in orbit around Earth or at a Lagrange point, astronomers could theoretically achieve resolutions several times better than the ground-based array. This mission concept is still in early development, but if realized, it could represent a significant leap forward. A space-based component would also eliminate the corrupting effects of Earth's atmosphere, which introduces noise and phase errors that complicate ground-based millimeter wavelength observations. Such a mission is technically challenging and expensive, but it represents the ultimate extension of the Event Horizon Telescope concept. The scientific potential of these future observations is immense. If current theoretical models are correct, they could allow unprecedented tests of general relativity, searching for deviations from Einstein's predictions that might point to new physics. Based on our understanding of galaxy evolution, such observations could reveal how black holes affect their host galaxies, feeding back energy and momentum that regulates star formation on galactic scales. They may also help solve the mystery of how supermassive black holes formed in the early universe, growing to billions of solar masses when the universe was less than 1 billion years old. Perhaps most excitingly, future observations could reveal phenomena that we have not yet imagined. The history of astronomy is full of examples where new observational capabilities revealed unexpected discoveries. When radio astronomers first turned their telescopes to the sky, they discovered pulsars and quasars, objects that were completely unknown. When gravitational wave detectors first achieved sensitivity to astrophysical sources, they detected merging black holes, confirming a phenomenon that had been predicted but never observed. The Event Horizon Telescope has opened a new window on the universe, and based on this pattern, we can reasonably expect that continued observations will yield surprises. As you listen to these words, the Event Horizon Telescope collaboration continues its work. Scientists are analyzing data from recent observation campaigns, developing new imaging algorithms, and planning future observations. Engineers are designing new telescopes and instruments that will extend the array's capabilities. Theorists are running simulations and making predictions for what future observations might reveal. Somewhere, at this very moment, radio waves that left the vicinity of a supermassive black hole millions of years ago are arriving at telescopes around the world. They carry information about the most extreme environments in the universe, places where gravity warps space and time beyond recognition, where matter and energy swirl toward an inevitable fate. With every observation, we learn a little more about these cosmic enigmas. The first image of a black hole was a triumph of human ingenuity and collaboration. It required the combined efforts of hundreds of scientists across dozens of countries, working together toward a common goal. It required pushing technology to its absolute limits, solving problems that seemed impossible only decades ago. It required patience, perseverance, and an unwavering commitment to understanding the universe. And it was just the beginning. The next time you look up at the night sky, consider what lies hidden in the darkness. In the heart of our own galaxy, 26,000 light-years away, a black hole 4 million times the mass of our sun awaits further study. In the distant galaxy M87, 55 million light-years across the cosmos, a monster containing 6.5 billion solar masses continues to devour matter and shoot jets of plasma across thousands of light-years of space. These objects, once purely theoretical, are now observable realities. We have seen them, we have measured them. We understand, at least in part, how they work, and in the decades to come, we will learn much more. The Event Horizon Telescope proved that seeing a black hole is possible. The next generation will show us what black holes do. And somewhere, perhaps in the future, that your children or grandchildren will inhabit, we may finally understand what black holes truly are. Consider for a moment what we have accomplished. Less than 5 centuries ago, humanity believed Earth was the center of the universe, with the sun, moon, planets, and stars revolving around us on crystalline spheres. Less than a century ago, we believed the Milky Way was the entire universe, with the fuzzy nebulae on the sky being minor features within our cosmic home. Less than half a century ago, black holes were still considered by many to be mathematical curiosities, objects that might exist in equations, but probably not in nature. And now we have photographed them. We have peered across 55 million light-years of space and captured an image of a region smaller than our solar system. We have measured the mass of an invisible object to within a few percent, using the size of its shadow as predicted by equations written more than a century ago. We have confirmed that the universe works the way our mathematics says it should, even in the most extreme conditions imaginable. This is the power of science, the ability to extend human perception far beyond the limits of our biological senses, to see things that evolution never prepared us to see, to understand phenomena that would have seemed like pure magic to our ancestors. The Event Horizon Telescope is the culmination of centuries of scientific progress, from Newton's laws of motion through Maxwell's equations of electromagnetism, from Einstein's theory of relativity through the development of radio astronomy and digital computing. But it is also a beginning. Every great scientific achievement opens more questions than it answers. We have seen a black hole, but we do not fully understand how supermassive black holes form or how they grow to such enormous sizes. We have confirmed general relativity in strong gravitational fields, but we know that general relativity must break down at the singularity, where a more fundamental theory is needed. We have imaged the event horizon, but we cannot see beyond it, into the region where space-time itself may cease to exist in any familiar form. Until then, we keep observing, we keep questioning, we keep pushing the boundaries of what is possible. The universe rewards our curiosity. Every time we develop a new way to observe the cosmos, we discover something unexpected. When Galileo first turned his telescope to the sky, he found mountains on the moon and moons around Jupiter, revelations that transformed our understanding of our place in the universe. When radio astronomers began scanning the sky in the 1930s, they discovered pulsars and quasars, objects unlike anything known from optical astronomy. When the Event Horizon Telescope achieved the resolution to image a black hole, it confirmed our theoretical predictions, but it has also opened questions about the detailed structure and dynamics of the plasma near the event horizon that will occupy astronomers for decades. What will we find when we point the next generation of telescopes at the cosmos? What will we learn when we make movies of gas swirling into black holes? What surprises await us when we push our instruments to even greater sensitivity and resolution? We cannot know. That is the beauty and the wonder of exploration. The unknown stretches before us, vast and mysterious, inviting us to continue the journey our ancestors began when they first looked up at the stars and wondered what they were. If you've enjoyed this journey to the edge of darkness, please consider supporting this channel with a like and subscribe. Your support helps bring these deep explorations of our universe to more curious minds around the world. Until next time, keep looking up, keep wondering, and remember that even the blackest holes in the cosmos cannot hide from human curiosity. Good night and pleasant dreams among the stars.